So welcome all in week 9 hydraulic engineering PMRF live TS session. Let me put it here for mic. I think fine. Okay. Welcome in week 9 hydraulic engineering PMRF live TS session. So in week 9 basically we discuss about loss in pipe flow and pipe networks, pipe in series as well as in parallel. Both we'll see, and we also solve lots of questions uh, regarding your assignment, and also I'll take some gate exam questions also, previous year gate examination, and Hardy cross method also we'll see. So before starting this lecture of pipe network, so basically why we need the analysis of the pipe network flow, because of already the water distribution, water supply through pipe. Another example, the oil supply, gas supply, so lots of things. So we need to analyze as a uh, as an engineer, so or as a civil engineer, we generally focus on designing of pipe for flowing the liquid, that is a water, sometime oil also. So what are the basic concept and basic principles for designing this kind of thing, and what type of losses, the loss in the bend, like near the valve, near the bend, we'll see everything. So basically here, first of all, we consider the laminar flow in pipe. So in practical, laminar flow is very difficult to maintain the laminar flow in the pipe. But for the concept point of view, we need to understand the laminar flow also as well as the turbulent flow also. So in practical, generally the turbulent flow, uh, generally in the application, we always see the flow is turbulent. Laminar flow is very rare. So these are the derivation we have discussed earlier also, just for your conceptualization or what how we proceed for the pipe losses. So that's why I have put it here. So laminar flow in pipe, basically you can see here the velocity diagram, very parabolic, and all in the previous class also I was discuss about the fully developed thing, fully developed flow. So all analysis what we will do in further slides and all, we all doing analysis, and we all do the analysis in the fully developed region. So what is fully developed region, you can prefer the previous video, but let me just for you, just I want to show you what is a fully developed flow. Let us, this is the pipe. So as entering the pipe, your velocity diagram like that. The diagram is not very clear. Here is very like that. Here is little bit less. Here is little bit less. Little bit. and after some distance your velocity diagram uh, is parabolic kind of thing, similar to this, and after that there is no change in the velocity diagram. Everywhere you can find, you will find the same velocity diagram. So up to that much distance from travel from initial position to up to the fully developed we known as the entrance length. So whatever we will do the analysis in this region, not in this region. So you can prefer the also standard book for that. So here the one derivation is, so sir has discussed very good manner, in very good manner. So please, or very conceptualized way. So please follow the lecture also, but just for your attention or some concept point of view I have put it here. So the average velocity in fully developed laminar pipe flow is half of the maximum velocity. So here is the concept. Sometimes this line is asked maybe in your assignment or somewhere in another exam. So you can expect this question. This is valid only for your circular pipe, not for all the geometry. If your pipe is circular and fully the pressurized flow, then this value is valid. U max is equal to 2 times of, or laminar also, not turbulent. If the same pipe, let us suppose you have two pipe, here is laminar flow and the similar pipe here is turbulent flow. So, and the velocity diagram you know already. In velocity diagram very parabolic in the your laminar, but here it not the same, little bit straight, then follow the parabolic. So this expression is valid for this pipe only. U max, that is the middle length, is equal to 2 times of average. Average means what? Average means everywhere you have considered the average velocity. Even here is 0, but you have considered some velocity. This is the average. So average every throughout the depth is same. So the meaning of average is, so it's 2 times. So here is some relationship. Using this relationship, this thing is correct. Because if r is 0, what will happen? If at the your expression derivation start from here, if your r is 0, that means you are at the center. So you are at the center means, so if you will put here 0, what will happen? So this will come and ur is will be the, at r is equal to 0, this is the maximum, because you are here subtracting something from 1, you are subtracting something. So if you will subtract 0, always 1. If you will subtract some, and negative value of r is not possible. So positive value, if you will subtract from here anything, then it will definitely be something, let's suppose 0.9, 0.8, point something. So this value will be the reduced. But if you will put r is equal to 0, then every this term will be the 0, or this term only, this term will be the 0, and 1 minus 0 will 0. 1 minus 0 is 1 again. So this is the your So what is the minimum value for subtracting from here is 0. So at 0 your velocity will be the maximum. So hope I think you got some good concept. Now moving ahead. So basically the head loss, or we have discussed lot about the your loss in the pipe in the previous class also. So one Darcy's Weisbach factor, or Darcy's Weisbach friction factor you can say also, or sometimes the Darcy's friction factor also. So this is actually one formula is there, like HL barabar, that is your head loss is equal to FL V square by 2ZD. If this is, then what will happen here? So this is only due to your friction of the pipe, and which is major, but some minor losses are also. So major loss only due to the friction, but minor losses having a lots of there are the different type of setup which will cause the minor losses in the pipe, whether valve, L junction, T junction, everything. We will see. For circular pipe, your F will be, if the flow is laminar or pipe is circular, though your F is equal to 64 by Re. But for if the laminar flow also, but same the circular pipe, your flow is not laminar, turbulent, then what will be the value of F? So for this, one Moody's diagram is there. The flow is turbulent in the pipe. What we are discussed earlier, this is same thing. These things also I have discussed earlier. So you can see here the velocity diagram. In case of laminar, you just see the straight, but here little bit straight, then follow the same thing. So here some very important points and everything is there. If you want to read, please try to read the all the sentence. It will be definitely enhance your knowledge or concepts. Pause the video and you can see. Now and how the Prandtl mixing length theory come, and how this your uh, analyze the your turbulent flow. In the turbulent flow, a viscous layer, buffer layer, overlap layer, then turbulent layer. These four type of layer. What is the four type of layer? So if you will read these things, then definitely you will be the fine. So we will not discuss here much, because we are in this video will talk about lots of problems as well as, and we are basically the focusing on the your pipe flow, pipe network analysis. So here the Moody's chart is for what? Your F value for turbulent flow. So this is the equation, and utilizing this equation one chart is given, this type of figure. Just you can see I have put it in the bigger slide. So this is your laminar flow up to that, but after that transient flow and the turbulent flow, and after these lines is the fully rough turbulent flow. Fully rough turbulent flow means what? Actually, even your Reynolds number is increasing in the fully rough region, but your friction factor is depend on what? Only these things. Suppose that your pipe material is like that, and your E by your E by D value is 0.006. this is, or your Reynolds number is 10 to the power 6, up to Reynolds number 10 to the power 6. So whether working or not. Yeah, it's recording almost. How many, or where we can see. Okay, here is showing the recording. Okay, that's fine. So okay, now we'll move ahead. So here is, sorry for some problem. So now what we have discussed here, actually this mood is diagram for what? Your roughness value, calculating the roughness value, that is friction factor for turbulent flow. So what is the value of friction factor in turbulent flow? So what we will do, let us, in the fully rough region, what, let me take some example. If your pipe is like that and your epsilon by d value is 0.006, so this is the 0.006 line. So if you will see this line and assume your Reynolds number is something like that, or 10 to the power, or you can take here also 10 to the power 6, your Reynolds number. So your roughness value will be what? Your roughness value will be 0 point something, 0.033, you can say. Your friction factor, your friction factor will be for this 0.033. Okay, so now if your Reynolds number is for same pipe, now we increasing the discharge and Reynolds number will be increasing up to the 10 to the power 7. Still, if Reynolds number is increased, then still your factor value, that is the friction factor value, will be the 0.033. So in fully rough turbulent region, there is no effect of Reynolds number. So only friction factor depend in the fully roughness region in your E by D, that is your relative roughness of the pipe. Now moving ahead, minor losses. So major loss due to the friction of pipe, your or roughness of the pipe. Now minor losses. So minor losses come from in fluid. The fluid in a typical piping system passes through the various fittings, valve, bend, elbow, tease, inlet, exit, expansion, contraction, in addition to the straight section of piping. So these all things you will be find in the pipe system. So these components interrupt the smooth flow of the fluid and cause additional loss because of the flow separation and mixing they induce. In a typical system with long pipe, these losses are minor compared to the head losses in the straight section, that is the major losses, and are called minor losses. Why we call the minor losses? This is the definition, because this is the very less. So here is very important one thing. What is actually we need to study the whole, let me read. Although this is generally true, in some cases minor loss may be greater than the major loss. Yes, may be possible, because it's depend on the lots of thing. It will be depend on how many your that is your fittings, how many valve, bend, elbow, tease. If so many, then definitely it may cause the more losses as due to the these kind of things. So this is the case. For example, a system with several turn and valve in a short distance might be possible. The head loss introduced by a completely open valve. For example, you may be negligible. What is it? The head loss introduced by a completely open valve, for example, may be negligible. Yes, we can assume. But a partially closed valve, if the your valve is partially, here is the example you can see. If the valve is partially closed, may cause the largest head loss in the system, as evidenced by the drop in the flow rate. Definitely, flow rate will be the drop. And the flow through valve and fitting is very complex, and theoretically analysis is generally not possible. Is not possible. So theoretically, actually, so therefore, okay, let me go. So theoretically not definitely. So therefore minor laws are determined experimentally, usually by the manufacturers of the component. So experimentally we determine. So minor losses are usually expressed in terms of loss coefficient KL, also called the resistance coefficient, defined as this. Your losses like that. HL KL, the loss coefficient is HL by V square by 2Z. So these all the definitions. So here one very important thing, your total loss is what? Your total loss, major loss, and the minor loss. So major loss you can calculate using the, here I indicate the pipe, which whether you are going for one pipe only, two pipe, three pipe. So summation of, at the place of I you will put 1 2 3 and you will add. So in a single pipe, if your pipe is like that, so this pipe have the major loss due to the roughness, and another the due to the your this bend. Due to this bend your minor loss will be there. So minor loss you will also calculate. So now the here everything you know already, but here how you will calculate this k value. So for calculating the k value, the lots of experiment as here we will see, therefore not generally not way not possible. So therefore the minor laws are determined experimentally. The lots of experiment thing is done, and we calculate k value is if your fitting is your pipe is like that, if is like that 0.5, if like that these things you please follow the every section you follow. And this is the sudden expansion and contraction based on a velocity in a smaller diameter pipe. So your sudden expansion value is KL value is this. KL is equal to alpha, that is alpha whole square 1 minus d square by d square. So here d is a small diameter and capital D is a big pipe, bigger diameter. So now here is one derivation. This is very important because I have the question based on this derivation actually. So how you will calculate your minor loss, that is in the sudden expansion? What you will do, this is actually your pipe, and here pipe your expand sudden, and water is flowing like center line. This is a center line, and you may section 1 and section 2 2. This is sudden expansion here. This is the case of sudden expansion. Okay, so how you will calculate? So first of all you apply the Bernoulli equation. When you will apply the Bernoulli equation, your formula will come like that. Hope I think it is visible. So your He is equal to, let me write here, I have written in, so P1 by rho z plus V1 square by 2z plus Z1 equal to P2 by rho z plus V2 square by 2z plus Z2. So Z1 is equal to Z2 here because the pipe is horizontal. So this will cancel out. So he and your loss will be there. And why we are adding loss here this side? Because of here is a that much energy, and you know already the energy cannot create or cannot destroy. So some losses is there up to that point, some losses, and some loss your fluid is travel from this location to this location. So some losses in the energy and whatever the remaining energy. So some losses and remaining energy will give the total energy at that point. So that's why we are adding this side only at the point 2. So this is the whole things. If you will calculate HL from here, what will be P1 minus P2 by rho z plus V1 square minus V2 square by 2z. So this is your loss. But now what is the value of P1 minus P2? So P1 minus P2 is nothing but your pressure at point 1 and point 2. So here pressure force is P1A1, and here pressure you know already, it is the compressive nature. So and P2, so that's why here compressive P2A2. So apply the Newton second law, that is the rate of change of momentum, and your momentum at that place, what will be your momentum? So your momentum will be rho 1, that is m dot v. So m dot v here, rho, your fluid density is constant, so rho, that is incompressible fluid, a, obviously why incompressible, because you have applied here the Bernoulli's equation and lots of assumption. I mean, if you are applying the Bernoulli's equation in any question, then you may by default you assumed all the assumptions. So here rho a, v for m dot, that is the mass flow rate, and another v also, so v1 v1. So here rho a1 v1 square, here rho a2 v2 square. So first of all, what is the force here, and here what will happen, one thing will be happen, your water will flow not like that, not the fully here, some space will be there. After travel up after some distance, your pipe will be completely filled with the water. Here some eddies formation will be there. Due to these eddies, some loss here might be, some losses. Here the energy losses. So this is area is experimentally, if you will see, this area is around A2 minus A1. And here one assumption is that, here one assumption is your here the losses force acting at that point is upstream force, that is the, here we will consider whether the P1 and P2, we will consider here P1, this is the assumption here. And after experimentally this thing will that is experimentally have seen, here generally we consider the P1, that is the your pressure force in the upstream direction, not the downstream. Experimentally also uh, researcher can see or have validated these things. So after applying the whole, your equation will become like that. Your force equation, when you will apply, so here all the derivation is given, you can go through that also, or I can explain. So here basically, uh, let me write the equation, if, because this is important. So your force equation will be what, your force equation is P1 A1 in this direction, summation of x, if it is, this is x direction, P1 A1 minus P2 A2 plus P1 A2 minus A1. This is the force. Force is equal to mass, that is the rate of change of momentum. MV. So your MV will be how much? Rho A2 V2 square minus rho A1 V1 square. So here what will be remain? So P1 minus P2 or here one thing will be cancelled out, P1 A1 will be the cancel out, only P1 P2 and A2 will be the common. is equal to, here you can also take the you can replace the a1 by a1 v1 equal to a2 v2. So your a2 is equal to, or a1 is equal to, because you want to keep a2 because it will be the cancel. So a1 v1 divided by, so you will put here, so you will get finally your p1 and p2 is equal to rho v2 square v1 v2. So you will be get this finally, and this thing you put in this equation. After putting this equation, you will be get he is equal to v2 square plus v1 square minus 2 v1 v2 divided by 2z. So these things you can write v1 minus v2 square, not v1 minus v2 whole square divided by 2. Also you can write v2 minus v1 whole square divided by 2, but here v2 is less, v1 is more. Here you can see, here the discharge, if your q1 is equal to q2, so a1 v1 is equal to a2 v2. So here a1 is less, so definitely your v1 will be the high comparatively. So we'll write these things. This equation will produce the negative loss, so we'll not consider this, we'll consider the v1 minus v2. But this will give the minus value, but no meaning. So now these are the again some losses, that is your sharp turn and the flane's elbow. So different type of experiment have done already. So now pipe network and pump selection. So pipe may be in parallel or maybe in series. So in series, basically here your loss in this pipe, your loss hf1, in this pipe your loss hf2. So total loss is how much? hf total is equal to hf1 plus hf2 in series. Definitely here will be the q1 is equal to q2. So this is the case of these two things in your series connection. So what will be the parallel connection? In the parallel connection, if you will see here, in the parallel connection what will be? Your discharge basically at point A, QA is equal to, in this pipe, let's suppose this is C and this is D, QC plus QD. But here the losses will be the equal, that is your hf1 is equal to hf2, I mean here C, hfc is equal to hfd. So remember these two things. In series your losses will be the add because of here two things, your same discharge here passing from this pipe to this pipe, or you can say, so that's why your continuity equation q1 is equal to q2. If some pipe from here, then your q may be the your, if some pipe was added here, then maybe your q will be the different, but here only one pipe going in this direction, so and it will meet, come at that and come at that, so this is this pipe parallel. So here is one very important concept. Might be some confusion due to one thing. So because here water is traveling in this direction and here water is traveling in this direction. So this pipe having the different loss, this pipe having the different loss. Your HF actually depend on what? FL V square by 2ZD, or you can say FL Q square by 12.1 d to the power 5. So your HF is equal to depend on length as well as your Q. Or maybe if your material is same, then this will be the constant. So this is a function of two things. If here your discharge is divided in two parts, let's suppose here Q was equal to 10. So here Q will be the maybe less than 10, maybe the your 5 or 3, or here maybe the your Q is here is the 3 and here is the maybe 7, so it will be the 10. So remember these things. So your loss will be in both pipe, in actually it's depend not only the length, because some confusion might be possible, because here uh, your loss should be also added, because water is traveling in this direction also, so loss will be the two times because it's traveling the more. Let us suppose one pipe is there and the same liquid I want to pass through this type of pipe. So one is here, one is here. So everything is same here in this pipe and in this pipe same, but here water is passing from two pipes, one pipe and two pipe, here in the single pipe. So someone can might be confused here. In parallel in this pipe water is and water is reaching at that point, so maybe your water is flowing in this direction due to that much covering that much length, and water is covering that much length, so here two times loss, that is here also water covering, here also water covering, definitely loss will be two times, but discharge is less compared to this pipe. So we will solve one question on that, so you will get very important concepts from here. So here one, now we'll solve some problems also from gate and everywhere, so we'll see everything. Okay, so now moving ahead on the question part. So here the first question is the head loss coefficient, that is your KL, what we are discussed earlier. KL in the sudden expansion shown in the figure below is proportional to. So sudden expansion, what was the formula? Your that is the HL is equal to KL V square by 2Z. So in the sudden expansion case, your formula was whole square by 2Z. So A1 V1 equal to A2 V2. So here you may put V2 is equal to what? A1 is equal to V2, or you will be find here V1. V1 is equal to V2 A2 divided by A1. Put in this formula. So your V2 A2 A1 minus V2 whole square divided by 2z. So here you can take the common. V2 will be the outside. So your value will be the A2 A1 minus 1 whole square divided by 2z. So here V2 square by 2z, and this is your KL. So what is KL? A2 by A1 minus 1. So V2 square by 2z. So if you will put A is equal to pi by 4 d square. So here A2 matlab capital D means, A2 means what? A2 means pi by 4 capital D square. A1 means what? Pi by 4 small d square. Pi by 4 and pi by 4 will be cancel out. So d square by small d square minus 1. So this is the your head loss. But so compared with this, so KL is equal to what? KL is equal to capital D square by small d square minus 1. So whether this is matching or not matching with any. So what you will do? So here now this HL what we have put here the in form of V2. So when you will calculate in form of V1, so your expression will come like that. Your small d is, let us calculate. So what you will do here, now we will find out the value of V2. So V2 will come A1 by V1 and A2 by A2. Your V2 will like that. So you will put in this equation. So when you will put, what will become? A1 V1 A2 minus V2 whole square divided by 2z. Oh no. At the place of V2 we will put. So your V1 minus A1 A2 V1 divided by 2z, and this is whole square. So your V1 will be the you can take the common, V1 square by 2z. Here is 1 minus A1 by A2. So now V1 square by 2z and your 1 minus D1, that is your D square and capital D square. So your KL is equal to 1 minus small d square by capital D square. So 1 minus small d square by capital D square to whole square. Definitely this will be the whole square. So your option is this correct. Option C is correct for that. So with this that kind of, you can take the approach. Just for why I'm taking the time on that, because it is very important how to calculate. So now the loss of energy at the exit of submerged pipe is what? The loss of energy at the exit of the submerged pipe. So these are the direct formula, that is your V square by 2G. Here another question. The loss of energy at the entry of submerged pipe. At the entry, here what the exit. At the entry, your formula is 0.5 V square by 2C. This is the value of KL. Here KL value is 1. Here KL value is 0.5. These all calculated based on experiment. So here it is given lots of things. Here KL value is given. Here KL value is given. Here KL value is given. So based on your question, you select the KL value or based on your application. So here it is very one important question. So let us some question from the Hardy cross method also here. So but before discussing more about the Hardy cross method, let us solve some question, because you know already sir has also discussed lots of things about the Hardy cross method. So we'll go one by one for solving this question. These are the GATE questions, GATE previous year questions. So first question is the head loss due to sudden expansion. The first question is the head loss due to the sudden expansion is expressed by sudden expansion, whatever the head loss. Head loss is equal to, we have discussed already, by 2G. Sometimes also V2 minus V1 whole square by 2G, but this will come in the minus. So this is the absolute. Or here is the square. So if you will minus this thing, automatically it will come positive. So no need absolute. So here is your option. I think D option is correct for that. So let me take a little bit highlighter. Red one. So your D option is correct here. Now moving ahead on the second question. The procedure to follow the solving the discharge when HF, your HF is given. HF given, pipe length is given, pipe length is given. Now D inside diameter is given. Now again your kinematic viscosity is given, and the wall roughness is also given. So how you will, the question is the procedure for solving the discharge. If these many data are there, so what is your procedure for solving? Option A, assume a friction factor, compute velocity, then Reynolds number, and then K by D, look up for F and repeat if necessary. So what you will do, you will assume the F first, then using the F you will calculate your HL loss, FLV square by and everything, FLV square by 2ZD. You will calculate these things using the HL, and from here your HF is given already, or HF you can say. So from here, oh why it is not working. So from here you can calculate Q, this equation, and Reynolds number. You know the Moody's diagram from here, and this side is E by D. that is the relative roughness. What is E by D? You just see here the relative roughness. So from Moody diagram you can calculate, and here is the Reynolds number and at this F. So now you will compare, you will if you will find Q, then you can also calculate velocity, and you will compare your Reynolds number and F value. If it is matching, then okay, otherwise not. The option B, what taking, assume R. Yes, not, we cannot assume R. So how we can assume the R, what will be the value of R in the pipe flow? So this is very difficult to assume velocity. Yes, this is not also convenient. So D, compute velocity and all, not. So option A is correct for that. This is the best procedure, because in this procedure no harm to consider the factor value, that is your friction value, because as per the material you can consider, but you cannot consider the your velocity or Reynolds number, because you cannot see by your eye whether the flow is that is laminar or turbulent. You can qualitatively find out, but quantitatively how you will find out how much you're turbulent and how much laminar. Now the branching, the branching in question number 3, branching pipe problem are usually solved. How? By assuming the head loss is the same throughout the each pipe, by equivalent the length, by assuming the elevation of the hydraulic gradient line at the junction point and trying to satisfy the continuity, by assuming the distribution which satisfy the continuity and computing direction. So which option is correct for that? So question number 7, branching pipe problem. So in the branching pipe problem we generally consider the continuity equation. Yes, definitely. So option D is correct for this question. So due to aging of the pipe, due to aging of the pipeline, it carries the capacity, its carrying capacity is decreases by 25%. So that is your discharge previously was Q. So now that is your Q1. So now discharge is 0.75 Q1. This is telling. Corresponding increase in the Darcy's-Weisbach friction factor. So what is corresponding increasing? The pipe is same and everything is same. How you will go? You know already the relation between your friction factor and all. Your HF is equal to, everything is same. So I will not write everything. Q square and F. You can write here. Because this F and L will be constant, D will be the constant, G will be the, everything will be the constant. So your HF1, so how you will calculate this thing? So let me take here, let me take eraser first. So erase the things, then I will discuss. So in question actually given your initially was Q and second time Q reduced by 25%, that means 0.75. So these two things is given and asking about your friction factor value, how much your friction factor increases, that is the friction of the pipe. So please think, very important concept. So nothing but initially was your discharge was Q, that is your friction factor was F. FL Q square by 12.1 D square. So this is the formula. So here asking about F. So F will be what? Is the directly proportional to 1 by Q square and everything will be the constant. So what is your new F? Or you can say this is the value of F. Everything is constant, let's suppose C. So what is the new? New is nothing but your C by 0.75 Q square. So C by 0.75 square Q square, and C by Q square you can write the 1 by 0.75 square into F. This is your new one. So how much? Let me calculate. So it will become around, I think, let me first check, 75 square. So it will come around 1.77 F. Your F new is equal to. So it means what? It means your value is increases by how much? This 0.77. 0.77 means how much percentage? 77%. Just imagine. Here the thing is your discharge carrying capacity increasing 25% only, but your friction factor increasing 77%. So question number 5 is what telling in network pipe, in the pipe network, and here is the concept. A algebraic sum of the discharge around each circuit is 0. Okay, let's see first. Option B, the algebraic sum of discharge around each circuit should not be 0. The elevation of hydraulic gradient line is assumed for each junction point, and the elementary circuit are replaced by equivalent pipe. So in network pipe, basically what are the concepts you just first read? In the pipe network, the following two rule must be satisfied. First rule, the algebraic sum of piezometric head. Here not discharge. Here we are talking about discharge, but piezometric head, that is your pressure head and the datum head, P by rho z plus Z. This is the piezometric head. Drop around each elementary circuit must be zero. Definitely must be zero, and how it will be zero we'll see in the Hardy cross method. And there cannot be any discontinuity in the piezometric head. Good. Second, the flow entering a junction or node must be equal to flow leaving at the same junction. Leaving the same junction. Let us first read. The flow entering a junction must be equal to the flow leaving the same junction. That is, law of continuity should be satisfied. If this, so the algebraic sum of discharge around each elementary circuit cannot be zero, because why? If it would be zero, then no net discharge would be available to pass into the next elementary circuit. That is, flow in the network would not be possible. So if it will be the zero in a circuit, so there is no flow to move in the next circuit. So your discharge should not be zero. So option B is correct for that. Now the question 7-6, that is question 6. While deriving an expression for loss of head due to sudden expansion, you are going to derive sudden expansion, which we have seen earlier also. In addition to the continuity and impulse momentum equation, we use the continuity equation. Definitely we have used a1 v1 equal to a2 v2, and momentum equation we also use, that is your pressure force is equal to change in momentum. Then one of the following assumption is made also. One of the following, which assumption we have made during the expression? So what, which one? A head loss due to friction is equal to the head loss is eddy motion. No, the main pressure in eddy fluid is equal to the downstream pressure. No, the mean pressure in eddying fluid is equal to the upstream pressure. Yes, definitely the mean pressure in the eddying, because we have what, during the derivation we assume these things. If this is flow, so this, so here is some eddies will form, and this here the pressure is how much? P1, that is we consider the pressure from upstream side, so upstream pressure. So option C will be the correct. And for 7.77, so this is also important. So let me first take the eraser, then I will talk about this important question. So what should be your approach for this question? So definitely when you will go thoroughly with the any derivation or concept, then you can find out the answer very easily and quickly. Otherwise, no other way to find out the answer of any question. So question 7, what exactly telling? Question 7 is telling you a single pipe of length L. A pipe is single, length L, diameter D is to replace by 3 pipe, is to replace by 3 pipe, same length and equal diameter. that is small d, or your small d is less than the capital D, is given in the question, and length is same. What was the length here? The length will be here also. All three pipe. Here was a single pipe and here three pipe. The second case. To convey the same discharge, same total discharge. Here is Q and here also. Water should convey only Q in both cases. Under the same head loss. Also head loss will be the same. HF here and HF loss here. Not 1 and 2. Here is a okay. Then D and D, that is your small d and capital D, is related to how it is related. So one thing you know already, HF I have discussed earlier also, HF1, HF2, HF3. So here all HF is same. So three HF for a small diameter, how you will write? FL V square or you can write here Q square divided by 12.1 capital D or a small d this side. Sorry. Small d to the power 5, and this side your this HF FL Q square, same discharge, 12.1 capital D to the power 5. So everything will be the cancel out. What only remain? 1 by d to the power 5 is equal to 3 d to the power 5. So your here you need relation in capital D. So your capital D5 is equal to d to the power 5 divided by 3. So your d is equal to, if will be go this side, 1 to the power 5. So option A is correct for that. This is very easy, not very tough thing, but you need to consider your single pipe is replaced in 3 pipe. Now let me take so in the next question what we will do, 7.8. 7.8 question is very easy, given very big picture, but if you will see very, let me take bigger one, highlighter. So this question, 3 reservoir A, B, C. 3 reservoir is given. Here elevation is 200, here elevation 180, and here elevation is 140. Shown in the figure. Water surface elevation in the reservoir and piezometric head at junction J, at this junction, is given 160. Here elevation is piezometric head 160. So the relation for this question, what will be correct? So whether Q1, Q2, Q3 relation, just you need to find discharge relation is just by following this figure. So what here is the discharge is to your elevation 200, definitely your water will be flow in this direction. Here your elevation is 180, here is 160, so definitely 180 or 160, so water will be flow in this direction. And finally here 140, so definitely here 160 and here 140, so higher elevation to lower, so higher energy to lower, so it will become. So your Q3 here and contributing Q2 and Q1. So your Q3 is equal to Q1 plus Q2, or Q1 plus Q2 is equal to Q3. So I think in the question Q1 plus Q2 is equal to Q3. So this is the final one. So option A is correct for this. Question 9, what telling? Question 9 is telling in the Bernoulli equation, what will be in the Bernoulli's equation used in the pipe, each term represent what? That is your P by rho z plus V square by 2z plus Z is equal to constant, is representing what? Energy per unit weight, energy per unit mass, energy per unit volume, or energy per unit length. Here I want to discuss one thing also, specific energy. We have discussed earlier in the fluid, that is your open channel class. So this is represent what? You can find out from here also. Here your specific energy term is representing what? That is energy per unit mass or volume or weight, and this representing what? Energy per unit mass, weight or volume, which one? So always remember, or a specific force also we can, specific force. Z bar A plus. Please just think, because this is very very important. Sometime people might be confused because somewhere the specific thing is used for related to volume, but here not the case. So the answer of this question is this Bernoulli's equation represents the energy per unit weight, and how energy, if you will, the unit of this equation is meter, and energy, that is your per unit weight, keep the unit of what? Meter. How? Energy is equal to work done, that is force into displacement. Weight is equal to Newton or mg. Mg is Newton, so this is also Newton. So only remaining d, that is your meter. But here this is meter cube, and this will also meter cube. And why we are talking, this is force. This term give the force per unit volume. Each term, each term represent the force per unit volume. Force per unit volume means Newton meter cube. And here meter cube is there. No, oh, this is wrong. Force per unit, this each term represent the force per unit weight of fluid. Unit weight. So force Newton and unit weight Newton per meter cube. It will come meter cube. So a specific force term, in a specific force, each term represents the per force per unit weight of the fluid. In here the same thing, weight per represent your energy per unit weight. So remember, sometimes people might be confused here. Specific force, sometimes people in without thinking much, people tell about this is a force per unit volume, but not force per unit weight of the fluid. So now moving ahead on the next question. This question from the your parallel pipe flow. But before discussing about this question, that is a parallel flow, we'll move ahead on the concept thing. So here it is very important question, or might be you can think this is a new question. A flow has parallel curved streamline. A streamline is curved and it is parallel, like that. This flow has tangential convective acceleration, local acceleration, normal as well as normal convective as well as local acceleration, or normal convective acceleration. So basically in curved, when the flow is in the curve pattern, what will be happen? Your particle is, when the flow is a straight line, your particle is moving only one direction. But here Your particle is moving in this direction, let's suppose here and here. Particle is moving in this direction also and vertical direction also, in both direction. So here the acceleration is that is one extra, that is one normal component of your velocity here. So that's why normal convective acceleration in the streamline, you can, the curved streamline always will be there. So option D is correct for that. Remember, the flow of a liquid at a constant rate in a conical trap tapered pipe is classified as, like that. Constant rate. Water is flowing at a constant rate in a conical tapered. So here what will happen? So whether it is a steady uniform flow, steady non-uniform flow, no, water entering from here is constant. So it is steady but not uniform, because at a particular time, at every section your velocity will be the different because it is tapered. So it is non-uniform stable flow. So these are some description. You can please go through, pause the video and read the line. Then you will get some your curved streamline acceleration. So these are the some what I was given here the question. So actually these are from the previous year gate question. So all solution is here. So please you go one. Oh, where is the solution? So please go one by one and you can find out the solution for this question here. So very easy. Everywhere, somewhere the parallel things, that parallel formula is applied. Somewhere is your calculation of your head loss. So very easy, not a big challenge to solving all these questions until unless here it is very important thing, that is your parallel water is flowing in this direction. Then what will be happen here? Your losses will be equal at the same places. So ratio of V1 and V2 will be the 2. So when you will read the question and solve every question, when you will solve this every question around 4 to 5 times, then easily you can solve gate question, coming gate question, that is your gate in 2025. You can easily solve related to the pipe law, but you need to solve the all question conceptually, all question conceptually, then easily you can calculate. Now moving ahead, this what I was discussed earlier, the curve streamline. Just remember one thing, here is the curve streamline, point A and point B. This is the stationary fluid and this is the flowing fluid, but this is the point A and point B. So point A pressure, that is point A, that is outer side, your pressure will be higher compared to this because of the what? Centripetal force, because of the centripetal force and centripetal acceleration due to this pressure gradient. So please go through this concept also. Now a triangular pipe network. This is question based on the Hardy-Cross method, and this is very important. The very single line answer for this question, but understanding behind this question is very important. So before solving this question, this is also gate question. I think gate 2017. I think you can see in the book. So we'll see this question before, and the answer is one line answer. But how you will get this concept before understanding the Hardy cross method, you're not able to solve this. So here is some concept, the Hardy cross method. Now one example I have also taken, so this will help you. So let us first discuss about Hardy cross method. Then we'll solve the question. So much time we have. We have around half an hour. So in half an hour, definitely we will cover the very in good way. So let me put it in the full view mode. So in the pipe network analysis, what we will do? So basically pipe network analysis, we have the lots of method, but here we are going to use the Hardy cross method for solving the pipe network. That is your Hardy cross method. So basically, and for solving the your problem, that is pipe network problem, so you need to calculate first the direction of the pipe flow. How you will find out the direction of the pipe flow? By simple observation. Let us suppose you can see the pipe from not inside, outside, then how you will find out the direction? So this is important. One of the how you will calculate the direction of the flow. The analysis is required, and hydraulic analysis definitely required. That is whether how much diameter, how much your velocity, and what is the roughness of the pipe, and which pipe is the suitable for the water flow and all. So this is very important. So let us suppose pipe network is nothing but your, suppose that your water is coming from a source, say reservoir. So it will be divided in different region by the pipe networking. So these are the nodal point or junction point. This is a reservoir, just for example. So if water is flowing here, Q might be here in this, let us suppose here the community is there. So in this community water will be going Q1. In this here water is going Q2. And this is junction for the future development. If any future development, this junction will provide the water in this direction. So let us suppose this is Q1, Q2, and this is Q3. So now, so this some basic had basically you can say the some basic assumption, not assumption, some basic principle to solve this pipe network analysis. So what is the principle? So let us suppose first principle is continuity equation must be satisfied at every junction. If this is junction, so continuity equation is satisfied at every junction. Like what is, if this is Q, so water is leaving from here, water is leaving from here in two direction, Q3. So your Q1, your Q should be equal to Q2 plus Q3. So this is the continuity. Another thing, the flow in each pipe And here is a very important thing I have written. Just please be bear with me, and I will discuss very unique thing, or that is not unique, but Hardy cross method. It's a very sometimes it is very difficult, but step by step, just please bear with me. You can feel very easy thing, the Hardy cross method, and one example we have also. So the second assumption is flow in each pipe must be satisfy the head loss equation, that is the Darcy's Bisbeck or Hazen-Williams equation. So what Hazen-Williams is given, that is your H is equal to Q to the power n, and in Hardy cross method you will be find everything will be the constant and your Q is square in the your this Darcy's Weisbach equation, that is your n is equal to Q2 in the Darcy's Weisbach. So this should be satisfied. Now the third one, the algebraic sum of head loss around a closed circuit must be zero. What actually this is telling? Let me draw some another. Let me take first eraser. So here is a circuit. Let me draw the circuit first. Here Q in, Q out. And let us suppose water is moving in this direction, and this is your clockwise direction. So generally we take the clockwise direction as positive. So you can take, but as per your assumption of the direction, you will be put positive or negative thing. But here we take the positive as a clockwise direction. Here is HL1 loss. Here is HL2 and here HL3. If this is like that, so your here the meaning of algebraic sum of head loss around any closed circuit must be zero. This is closed circuit. So head loss here was the, let us suppose initially your total head was capital H. So this minus of all this head loss, all this whatever the head loss, that is H1 plus H2 plus H3 must be zero. Or if it is flowing in this direction, let me erase, then some important concept I can tell here. If it is flowing in this direction, if water is going in this direction, this is HL3, and coming in this direction and going in this direction, what will happen? If it is not zero, zero means what? Zero means your H is equal to H1 plus H2 plus H3, HL1 HL2. If it is not zero, then you cannot equalize these two things. So if it is not equal, you need to apply some correction for equalize. So the condition for the third condition is algebraic sum of the head loss around a closed circuit must be zero. So this is the assumption. So this is the basic concept. Now, based on this some basic principle or basic concept, so on Hardy Cross in 1934 developed a method that is the successive approximation method, based on approach of the successive approximation. So step first was what? So basically he has given the steps. So first, the most reasonable discharge in each pipe is assumed satisfy the continuity condition. So basically what you will do, if your circuit is like that, your network is like that, so you will be consider a reasonable discharge in each pipe. Let us suppose in this pipe is Q naught, in this pipe is Q naught 1, in this pipe Q naught 2. So like that you will be assume. Head loss in each pipe is computed by the Hazen-Williams equation. You can use the Hazen-Williams or you can use the Darcy-Weisbach. In the equation or in the question, it will be defined already. Like in this question, you can see here, your head loss is computed not as per the HF is equal to R, or you can write K also, Q to the power 2. Here is 1.8. So Darcy-Weisbach not here we have followed. So it will be defined in the question already. Maybe the Hazen-Williams or sometimes Darcy-Weisbach, or maybe the another also based on experiment. Summation of head loss around a closed loop is calculated by considering clockwise flow as positive and anti-clockwise is negative. So this is we are going to assume. Sometimes you can take the anti-clockwise positive and clockwise negative, but here generally clockwise we can take the positive. Remember, clockwise we will consider positive. Now, in order to satisfy HL, that is your summation of your head loss is equal to 0, the flow is adjusted by applying the correction A delta Q. So now how you will calculate your delta Q, that is your correction discharge, because initially we have assumed your discharge Q, that is Q naught, but this is not correct. We need to provide the actual one, and how we will calculate this actual one. So your actual discharge may be your corrected discharge, you can say your Q naught minus something whatever you have applied the correction thing. Sometimes it will be add, sometimes it will be minus. That is your correction. This is your corrected one. So Q naught minus. So this is. So your HL is equal to what? HL is equal to K Q to the power N. And here K is your Q is what? Q naught minus delta Q to the power N. Using the Taylor series, what you will get? You will be the get K, that is your Q naught to the power N minus N Q naught to the power N minus 1 delta Q. The other term, what you will get? The plus delta Q square. So higher term we may neglect because your delta Q should be the very least. So your HL finally what will come? Okay, that's why we are telling here the approximation success. approximation value it will give, because we are neglecting something. So k is equal to q to the power n minus n q naught n minus 1 delta q. So from here, so for a loop your delta L will be the 0. If delta L will be the 0, what you will get? K qn minus n q naught n minus 1 delta q is equal to 0. So your delta q will be what? Summation of, suppose that lots of your pipe network is there in the loop, lots of pipe members. So summation of k, or assume n is equal to 2. We are assuming the, that is Hardy cross, that is your Darcy's Weisbach. So n is equal to 2. So k q square divided by summation of this n is equal to 2. So 2k q naught. So remember, this is the whole derivation, and you can follow step by step here also. You can easily get this summation thing. We will put positive or negative as per the direction of flow, whether it is plus direction or whether it is that is your clockwise or anti-clockwise. So based on that, and after that you will apply the check also. In case of member, let's suppose on common member like that, in this loop this line is coming, and in this loop also this member is coming. For common loop you will be the check, you need to check the apply whether it is positive, whether it is some, from this loop your correction value will be the minus, or from this loop your correction value will be the minus or plus. You need to check and repeat of first letters, and the condition of summation of L should be checked with the revised flow after applying the correction. Definitely it will be the check. The procedure need to be repeated until the your accuracy obtained, desired accuracy, that is your delta q should be less, least. So this is whole idea. One question here I have solved, but before this we need to solve the gate question. So please read the question first. A triangular pipe network is shown in the figure. Let me take water some. Please read the question and try to solve. So actually in this question, a triangular, that is k, somewhere we have written the k, but here r you can also write. This is a constant thing. It will depend on the pipe material and length and everything. So a triangular pipe network is shown in the figure. The head loss in each pipe is given by HF is equal to R Q to the power 1.8, with the variable expressed in a consistent set of unit. Okay, that is the unit consistent. The value of R for the pipe AB, 1, and for pipe BC is 2. If the discharge supplied at point A is 100 and equally divided in the pipe AC, AB and AC, that is here 50 and here also Q2 is equal to 50. So definitely it will go this side, because 50 here leaving the 30, then remaining 20 will go this side, and definitely. Now the value of R up to 2 decimal place for the pipe AC should be need to calculate. So the R value here asking about this. So what we will do? So you know one thing, in a closed circuit your head loss will be the 0. Summation of HL will be 0, or summation of HL will be 0, or HF here it is written, you can write also. So how you will write? Let us suppose clockwise here, we going to take the positive clockwise. So your R1 Q1 here is, this is just opposite, that is anti-clockwise, minus R2 Q2. Let us suppose this is Q3. Here is clockwise in this direction, but this is also negative, so minus R into Q2 equal to 0. So R1 value is how much? R1 is 1, Q1 is 50, power 1.8 is everywhere. So your R2 value is how much? Your R2, this is, let's suppose this is R2, then R2 2 into 1.8 power here. Q3, that is your, this is Q3. Q3 is how much? Here is 30 leaving, this side will be go 20. So your 20 power 1.8 minus R need to calculate, and Q2 is 50. And after that, when you will calculate, your R will come around 0.615. So you need to put here up to 2 decimal, so your correct value will 0.61. Or you can also write 0.62 also, because in the your answer some range will be there. Depend on the your sensitivity of the range, the range will be the provided in the question. So this type of question you can expect in your exam or final exam. So please try to go through the all concepts before solving the any. Let me take one question from this side also, that is your this book. So let me take the question number 70, because this is of we have discussed a lot from the series pipe, some parallel question, the parallel network also. A incompressible fluid, incompressible means rho will be the constant throughout, is flowing a steady rate. Okay, steady flow is given. Horizontal pipe, that is theta will be the 0. From a section, the pipe divided in two horizontal parallel pipe. It is divided in two horizontal. Two horizontal pipe. Okay. D1 and D2, where D1 is equal to 4D2. If this is D1, or if this is D2, then this is 4D2. So this is D1 and this is D2. The run for a length L each, and then again join back to the a pipe of original size. If here was diameter T, then original size here diameter T. For the both parallel pipe, assume the head loss due to the friction only and Darcy's-Weisbach friction factor to be the same. Okay, F is the same, that is for both one. F1, F2 is the same. Due to the friction only head loss, that is your major loss here you need to consider, not any the bend loss or other losses, sudden expansion, contraction. The velocity ratio between the bigger and smaller, that is bigger means what, this is smaller because d2 here the 4 time, so that is your v1 minus v2, bigger one means v1, that is v2. So you need to calculate this thing. So from parallel pipe, you know your head loss is equal to in both pipe, that is in this pipe and this pipe, your head loss will be the equal. This is the main concept here. But you can think one thing is very important. Here is the discharge in the length is same. Here the length is L, this is length is L, and this is length is L. Both side length is L. Water is traveling the same length. Then how can we assume the discharge will be the, your head loss will be the same in both? Yes, length is L. Then you can, using the length you can tell about the your discharge will be the your head loss will be the same. But here diameter is different because HF is depend on what 4, that is FLV square by 2ZD. It depend on diameter also. It depend on discharge also. It depend on length also. Length is constant, F is constant, but here one diameter is less and one diameter is high. Here the discharge in one, in this one is discharge definitely will be the less compared to less. So it will be incorporated, and it will be incorporated like that in both your, in this and in this direction, that is your in both parallel pipe, your head loss will be the same. HF1 is equal to HF2. So easily you can put it here. Length will be same. So discharge, that is your velocity here, q1 square divided by 2z will be the same. So d1 here, v2 square divided by d2. So your d2 d1 is equal to 4d2. So d2 d2 cancel. So here it will remain v1 by v2 is what? 4 or square. So v1 by v2 is equal to 2. Very easy. 2 marks. So when you know the concept and everything, you can very easy or very easily you can solve the questions. But you need to the concept and all. So with that we can go also some another question, but all question is very easy. So please try to solve the question as much as possible, then you can get definitely confident. So here you no need to know the all remember all the for this k value, because in any question uh, generally k value is given, because how much will be the this form, this derivation is very important sometime. Okay, so with that and this Moody's diagram always remember, because people forget about it how we will calculate the HF sometimes when we will leave this fluid mechanics course, your fluid mechanics course, after some time you will be forget about how we will calculate your friction factor in the turbulent flow, in the flow like turbulent. So always remember the Moody's diagram or this Colebrook equation. Colebrook equation you can. So lots of development already done in the fluid mechanics, and still development is going on. So here the velocity diagram you can see in case of turbulent flow how it is behaving. Here is linear, then after parabolic. So remember these things. The Prandtl mixing length theory is very important theory for turbulent flow. So remember, need please very carefully all these things. Okay, thank you for today.